Assalamu alaikum. Today we'll be starting chapter number 30th of Survey and Jude, and we'll complete article 30.1 today and related examples. Article 30.1 is about Biot-Savart Law. Uh, some of the main points of Biot-Savart Law is that these are the two scientists who worked on this current carrying conductor and conducted different experiments, and then they formalized a formula in which they said that changing magnetic field depends upon current and the length element as well as the radial direction. So they conducted quantitative experiments on the force exerted by a current on a on a magnet which is placed in the near vicinity. So from their experimental result, they arrived at a mathematical expression that gives magnetic field in terms of current that produces it, and at some point in the space. Before formalizing, we have to consider these following points. Point number one is that this change in magnetic field, a very small change in magnetic field, is perpendicular to both the length element, that is ds over here, and it is also perpendicular to the unit vector r, that is directed from the length element towards a point P. If you look at this figure, then we have this conductor over here. The current is in this direction, and obviously the direction of the length element is in the direction of the current. So this is the direction of this length element ds, and we have to calculate b over here, that is db over here, that is at point P. And this db, if we consider the direction of ds and the direction of the point P at which we have to calculate b, if we take the direction of these two, then this b is coming out of the plane, that is out of the screen of the laptop. So we have to calculate this db, and this db is perpendicular to the length element as well as unit vector r. Magnitude of dB is inversely proportional to r square. That is the distance of the point at which we have to find this changing magnetic field. Uh, the magnitude of this changing magnetic field is inversely proportional to the distance from the current carrying conductor. So obviously, if we move away from the current carrying conductor and suppose we move at a distance infinity, then dB will be equals to 0, because as we increase the distance, the effect of the current carrying conductor producing magnetic field in its vicinity will decrease. So with distance, dB will decrease and eventually will die. Magnitude of dB is directly proportional to current and to the magnitude ds, that is the length element, and so we can write that this dB is directly proportional to s and is directly proportional to ds, as well as the magnitude of this changing magnetic field is also directly proportional to the sine of the theta, which is the angle between this length element and unit vector r. So uh, this changing magnetic field is directly depending upon IDS and sine of theta. Now, keeping in view the above mentioned points, we can write this formula over here, that is dV is directly proportional to I, to ds and unit vector r, but is inversely proportional to this r square. That is, as we increase the distance of the point where we have to calculate the magnetic field from the current carrying conductor, the magnetic field will die. So as this is the cross product between ds and unit vector r. So if we simplify it, we get ds sine of theta, because unit vector r is equals to 1. So we get this ds sine of theta, and from here we can see that this dv is also depending upon sine of theta. So to remove this proportionality sign over here, we have to introduce a constant, and this mu naught over 4 pi is a constant, and mu naught is known as permeability of free space, and the value of mu naught is 4 pi into 10 raised to the power minus 7 Tesla meter per amps. And as I said before, it's permeability of free space. So we have used this constant to remove this proportionality sign over here. Now ds is very small length element. To find the effect of a whole wire in producing the magnetic field, we have to integrate equation number 1, that is this equation over here. So if we integrate it, we get the total magnetic field, that is B is equals to mu naught I over 4 pi integral ds cross unit vector r over r square. So this is Biot-Savart law, and this is basically they have contributed to the mathematical formula after conducting several number of experiments. Now we will go through certain 3 different examples and apply this Biot-Savart law on different scenarios. So example 30.1 says that consider a thin straight wire carrying a constant current I and placed along the x-axis. So the conductor is placed along the x-axis. Determine the magnitude and direction of the magnetic field at point P. So we have to find the magnitude and direction of the magnetic field at this point due to this current carrying conductor. So this is the current carrying conductor and is placed along x-axis. This is point P over here, and these are the names given to different sides of the triangle which we have drawn over here. So this is A, that is the vertical distance of point P from the conductor, and this is X, as this X is in the negative side. So you'll see that at some point we will use a negative with this X over here, and R is pointing in this direction, and A is also pointing in this direction, and this is, so by using head to tail rule, you can see that we have drawn this vector originating from left and moving towards right. Here we have drawn this vector A that is pointing in the positive y direction. So we have placed the tail of this vector and drawn it in this direction, and to get the resultant we have drawn this vector over here, that is by joining the tail of the last with the tail of the first and head of the last with the head of the first vector. So we have completed this triangle by using head to tail rule. Now from here we can see that if I take this is the length element, and the direction of the current is towards the x direction. So if I take the mod of this ds, so as I am considering a very small length element and the direction in which the current is moving, so this I can represent this length element as dx. So in the formula I'll replace ds with dx. Now if I see that I have angle theta over here, and this is a right angle triangle. So if I want to find sine of theta, suppose what will I do? I will use basic trigonometric rule, that is perpendicular over hypotenuse. So and so on. So let's start solving the problem. So at point P we have to find B, and using this Biot-Savart law, I have considered this part of the formula currently. So ds cross unit vector r is equals to ds cross unit vector r unit vector k. So if the length element is pointing in x direction and the unit vector r is pointing in the y direction, then obviously their product will be pointing in the z direction. So that is why I have unit vector k over here, and simplifying it, replacing this ds with dx, and dx sine of theta unit vector k, as unit vector r is equals to 1. So now writing the formula, that is dv is equal to mu naught I over 4 pi dx sine of theta over r square unit vector k. Now this is the magnitude of dv. So here I can remove this direction, and now I want to calculate the magnitude of dB at point P. So for that I have mu naught I over 4 pi dx sine of theta over r square. From the triangle, sine of theta is equals to a over r, as I have told you before that this is the perpendicular and this is the hypotenuse, so I can write a over r. So this is what I have done over here, that sine of theta is equals to a over r. From here I can find the value of r, which is equals to a sine of theta, and if I have 1 over sine of theta, I can write it as cosecant theta. So I have a cosecant theta. Also, if I want to find the tangent of theta over here, so what I'll do is from this triangle again, I know that tangent of theta is equals to perpendicular over base. So the perpendicular here is A, and the base is in the negative x direction, so that is why I have written minus x. So tangent of theta is equals to perpendicular over base, so a over minus x. So I can rearrange this as x is equals to minus a cot of theta. That is taken this x to this side, and dividing tangent of theta with a. 1 over tangent of theta is equals to cot theta. So I can write minus a cot theta, as I have dx in the formula. So I'll take derivative on both sides. So dx is equals to, when I take cotangent minus cotangent theta d theta, I'll get cosecant square theta d theta. So this is what I get over here, and from equation 2 and 3 I can easily modify equation number 1, that is the Biot-Savart law. So putting in the values of dx, I have replaced dx over here with a cosecant square theta, and sine theta d theta over r square is a square cosecant square theta. So cancelling the values over here, and I simply get dB equals to mu naught I over 4 pi sine theta d theta over a. So now I want to find the total magnetic field. For that I'll integrate it, and I'll integrate it by giving the limit theta 1 to theta 2. So when I integrate sine of theta d theta, I get minus cos of theta with limit theta 1 to theta 2. Putting in the limits, the value for b will be mu naught I over 4 pi a into cos of theta 1 minus cos of theta 2. So let us take the extreme values, that is when theta 1 is 0 and theta 2 is pi, then 1 minus 1 will give me 2, and I have B is equals to mu naught I over 4 pi A into 2, which will give me mu naught I over 2 pi A. So this is how we can calculate the magnetic field which is being produced by a conductor, which is placed horizontally along the x-axis, and finding the magnetic field at point P, which is placed at a certain distance away from this current carrying conductor. So in example 2, uh, okay, now example 30.2. Calculate the magnetic field at point O for the current carrying wire segment. The wire segments of two straight portion and a circular arc of radius r, which subtends an angle theta. The arrowheads on the wire indicates the direction of the current. So look at this figure over here. The current is moving from A prime to A, then will move in this arc, and then we'll move from C to C prime. So if you look at the length element ds and ds over here, uh, the direction of the length element and the direction of unit vector r, they are for a prime and r, theta is equals to 0, and for c prime theta is equals to pi or 180. So sine of 0 and sine of pi will give us 0. So these two segments are not contributing to the magnetic field. So the contributing factor will be this AC over here. So now from here I have extended these lines and meeting at over here. The radius is given by capital R, and the unit vector r is pointing towards the origin. So, and this is the angle theta over here. So I can consider this to be the arc length of this portion, is acting as an arc length over here. So I'll treat it as an arc. Okay, now to find dB, what will I do? I'll simply write the Biot-Savart law, that is mu naught I over 4 pi ds over r square. So unit vector r, if I write the cross product of unit vector r, the angle is 90, so 1 into sine of 90 will give me 1. So now I can take the mod, and I have written it for the magnitude. So now integrating it, after integrating I get b equals to mu naught I over 4 pi r square, and after integrating this ds, I can write this as s, where s is the arc length, and we know that arc length is equals to r theta. So putting in the value of this arc length r theta, simplify it, and I can find the magnetic field, that is mu naught I over 4 pi r theta. So this is how you can find the magnetic field if you have a situation like this, that whenever you have some length element which is placed in a curve. So this is how you can easily find the magnetic field. Okay, in the third example, consider a circular loop. Now we have a complete circular loop of radius r located in the YZ plane and carrying a steady current I. Calculate the magnetic field at an axial point P, a distance x from the center of the loop. So now let us suppose that this is a loop over here, and this is the length element in this direction, and the unit vector r is in this direction. So we have radius capital R, and if I want to find the magnetic field at point P over here, I can complete this right angle triangle sorry, just let me, okay, so I can complete this right angle triangle to make calculation easy. Okay, now I actually what I have to do is to find the magnetic field at this point P. uh, at this point we have two components of magnetic field, that is along y axis and along x axis. Uh, the magnetic field along y axis will cancel the effect of each other, and overall field along this direction will be 0. So the main contributing factor for magnetic field will be along x axis. So for that we will proceed as again considering this part of the Biot-Savart law, that is ds cross unit vector r is equals to ds, as theta is 90 and unit vector r is 1. And again from the equation we can use the Pythagoras theorem, that is hypotenuse square of hypotenuse is equals to square of the perpendicular plus square of base. So r square is equals to x square plus r square. And from Biot-Savart law we can write this r square and replace this r square with x square plus r square. So I can write dB is equals to mu naught I over 4 pi multiply by ds over x square plus r square. dB is perpendicular to the plane formed by S and R. So we have already seen in example number 1 that ds and r, if they are in suppose x and y plane, then dB will be in the z plane. So dB will be in the plane perpendicular to a length element and unit vector r. Resolving B into components, so I have told you that dBy will not contribute. If I'll sum up all the elements, they will give 0, so the contributing factor is bx. So b is equals to bx unit vector I, and again I can write this bx as b cos of theta. So as we are considering small elements right now, so I will use dB over here. So dx is equals to closed integral dB cos of theta. Simply replacing the value of dB, that is mu naught I over 4 pi closed integral ds over x square plus r square cos of theta. From the triangle we can also find the value of cos of theta. We know that cos of theta is equals to base over hypotenuse. So if you look at the triangle over here and look at the figure, okay, so if you look at this figure, there is an angle over here as well. So this is the base, and this is the perpendicular, and this is the hypotenuse, considering this angle over here. So if I now want to calculate cos of theta, so base over hypotenuse, so r over r, capital R over small r, and we know that small r is equals to x square plus capital R square, so under the rule. So here I can easily replace this cos of theta using this r over capital R over small r, and small r is x square plus r square under the root. Now putting this value in this equation, so we'll be getting bx is equals to mu naught I over 4 pi closed integral r over x square plus r square 3 by 2, because 1 by 2 plus 1 will give me 3 by 2. So we have to apply this closed integral over this ds, and this will give me the circumference of the loop, that is 2 pi capital R. So putting in the value and simplifying it, I'll get mu naught I over 2 r square over r square plus x square 3 by 2. So if x is 0, then we'll get Vx is equals to mu naught I over 2r. So by varying this x, that is the distance of the point, we can vary the value of this magnetic field. So this is all about Biot-Savart law. I hope you all understand.